The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let's start. So, we are back to calculating partition functions for Ising models. So again, some in general hypercubic lattice where you have variables sigma I being minus plus 1 at each side with a tendency to be parallel. And our task is to calculate a partition function which for n sides amounts to summing over 2 to the n binary configurations of a weight that favors near neighbors to be in the same state with a strength k. Okay? So the procedure that we are going to follow is this high temperature expansion. That is writing this as hyperbolic cosine of k 1 plus t standing for tanh k sigma I sigma j. And then as we discussed, actually this I would have to write as a product over all bonds. And then essentially to each bond on this lattice, I would have to either assign 1 or t sigma I sigma j. Binary choice, now move to bonds. And then we saw that in order to make sure that following the summation over sigma, these factors survive, we have to make sure that we construct graphs where out of each side go out an even number of bonds. And we rewrote the whole thing as 2 to the n cosh k to the number of bonds, which for a hypercubic lattice is dn. And then we had a sum over graphs where we had an even number of bonds per site. And the contribution of the graph was basically t to the power of the number of bonds. So I'm going to call this sum over here S. After all, the interesting part of the problem is captured in this factor S. These 2 to the n cosh k to the power of dn are perfectly well-behaved analytical functions. We are looking for something that is singular. So this S, I can either pick 1 from all of the factors. So to the lowest order in t, I would have to put 1. And then we saw that the next order correction would be something like a square, would be this t to the 4th. And then objects that are more complicated versions. And I can write all of those as a sum over kind of graphs that I can draw on the lattice by going around and making a loop. But then I will have graphs that will be composed of 2 loops, for example, that are disconnected. Since this can be translated all over the place, this would have a factor of n for a lattice that is large for getting side effects and edge effects. This would have a contribution once I slide these two with respect to each other that is of the order of n squared. And then I would have things that would be 3 loops and so forth. Now, based on what we have seen before, it is very tempting to somehow exponentiate this sum and write it as exponential of the sum over objects that have a single loop. And I will call this new sum actually S prime for reasons to become apparent, because if I start to expand this exponential, what do I get? I will certainly start to get 1, then I will have the sum over single loop graphs plus 1/2 whatever is in the numerator or in the exponent over here squared, 1/3 factorial, whatever is in the exponent, which is this sum cubed, and so forth. And if I were to expand this thing that is something squared, I will certainly get terms in it that would correspond to 2 of the terms in the sum. Here I would get things that would correspond to 3 of the terms in the sum. And the combinatorial factors would certainly work out to get rid of the 2 and the 6, etc., depending on, let's say I have loop A, B, or C. I could pick A from the first sum here, B from the second, C from the third, or any permutation thereof that would amount to C. I would have a factor of C, A, B, C. But S definitely is not equal to S prime, because immediately we see that once I square this term, A plus B squared in addition to A squared AB, I will also get A squared and B squared, which corresponds to objects such as this. 1/2 of the same graph repeated twice. Right? It is the A squared term that is appearing in this sum. And this clearly has no analog here in my sum S. I emphasize that in the sum S, each bond can occur either 0 or 1 time. Whereas if I exponentiate this, you can see that S prime certainly contains things that potentially are repeated twice. As I go further, I could have multiple times. Also, when I square this term, I could potentially get 1 factor from 1, another factor which is also a loop from the second term in this product of 2 brackets, which once I multiply them happen to overlap and share something. Okay? All right. So very roughly and hand-wavingly, the thing is that S has loops that avoid each other, don't intersect, whereas S prime has loops that intersect. So very naively, S is sum over, if you like, a gas of non-intersecting loops. Whereas S prime is a sum over gas of what I could call phantom loops. They're kind of like ghosts. They can go through each other. Okay? All right? So that's one of a number of problems. Now, in this lecture, we are going to ignore this difference between S and S prime and calculate S prime, which therefore we will not be doing the right job. And this is one example of where I'm not doing the right job. And as I go through the calculation, you may want to figure out also other places where I don't correctly reproduce the sum S in order to ultimately be able to make a calculation and see what it comes to. Now, next lecture, we will try to correct all of those errors. So you better keep track of all of those errors. Make sure that I am doing everything right. Seems good. All right? So let's go and take a look at this S prime. So S prime, actually log of S prime, is a sum over graphs that I can draw on the lattice. And since I could exponentiate that, there was no problem in the exponentiation involved over here. Essentially, I have to, for calculating the log, just calculate these singly connected loops. And you can see that that will work out fine as far as extensivity is concerned, because I could translate each one of these figures of the loops over the lattice and get the factor of n. So this is clearly something that is OK. Now, since I'm already making this mistake of forgetting about the intersections between loops, I'm going to make another assumption. That is, in this sum of single loops, I already include things where the single loop is allowed to intersect itself. For example, I'm going to allow as a single loop entity something that is like this, where this particular bond will give a factor of t squared. Clearly, I should not include this in the correct sum. But since I'm ignoring intersections among the different loops and I'm making it phantom, let's make it also phantom with respect to itself, allow it to intersect itself also. It's in the same spirit of the mistake that we are going to do. OK? So now what do we have? We can write that log of S prime is this sum over loops of length L, and then multiply it by t to the L, right? So basically, I say that I can draw loops, let's say, of size 4, loops of size 6, etc. Each one of them, I have to multiply by t to the L. Of course, I have to multiply with the number of loops of length L. OK? And this I'm going to write slightly differently. So I'm going to say that log of S prime is sum over this length of the loop. All loops of length L are going to contribute a factor of t to the L. And I'm going to count the loops of length L that start and end at the origin, and I'll give that a symbol WL00. Actually, very soon, I will introduce a generalization of this. So let me write the definition. I define a matrix that is indexed by two sides of the lattice and counts the number of walks that I can have from one to the other, from I to j, in L steps. So this is number of walks of length L from I to j. OK? So what am I doing here? Since I'm looking at single loop objects, I want to sum over, let's say, all terms that contribute in this case, t to the 4, it's obvious because it's really just one shape. It's a square. But this square, I could have started at anywhere on the lattice. And this slight factor, which captures the extensivity, I'll take outside because I expect this log of s to be extensive. It should be proportional to n. So one part of it is essentially where I start to draw this loop. So I say that I always start with the loops that I have at point 0. Then I want to come back to myself. So I indicate that the endpoint should also be 0. And if I want to get a term here, this is a term that is t to the 4th, I need to know how many of such walks I have. Yes?
Are you allowing the loop to intersect itself in this case or not?
In this case, yes, I will also, when I'm calculating anything to do with S prime, I allow intersection. So if you're asking whether I'm allowing something like this, the answer is yes.
Okay.
Yeah.
And are we assuming an infinitely large system so that?
Yes, that's right. So that the edge effects you don't have to worry about, or alternatively, you can imagine that you have periodic boundary conditions. And with periodic boundary condition, you can still slide it all over the place. Okay? But clearly then, the maximal size of these loops, etc., will be determined potentially by the size of the lattice. Now, this is not entirely correct because there is an overcounting. This one square that I have drawn over here, I could have started from this point, this point, this point. And essentially, for something that has length L, I would have had L possible starting points. So in order to avoid the overcounting, I have to divide by L. And in fact, I could have started walking along this direction, or alternatively, I could have gone in the clockwise direction. So there's two orientations to the walk that will take me from the origin back to the origin in L steps. And not to do the overcounting, I have to divide by 2L. Yes?
If we allow walking over ourselves,
Yes.
is it always a degeneracy of 2L? In the
Yes.
sense
You can go and do the calculation, etc., to convince yourself that even for something as convoluted as that,
still
you
2L.
can, it is 2L. Okay? So this is what we want to calculate. Well, it turns out that this entity actually shows up somewhere else also. So let me tell you why I wanted to write a more general thing. Another quantity that I can try to calculate is the spin-spin correlation. I can pick spin 0 here and say spin r here, some other location. And I want to calculate what is the correlation between these two spins. Okay? So how do I have to do that for the Ising model? I have to essentially sum over all configurations with an additional factor of sigma 0, sigma r of this weight e to the k sum over ij, sigma I, sigma j, appropriately normalized, of course, by the partition function. And I can make the same transformation that I have on the first line of these exponential factors to write this as a sum over sigma I. I have sigma 0, sigma r, and then product over all bonds of these factors of 1 plus t sigma I, sigma j. The factors of 2 to the n cosh k will cancel out between the numerator and the denominator. And basically, I will get the same thing. Now, of course, the denominator is the partition function. It is the sum s that we are after. But we can also, and we've seen this already, how to do this, express the sum in the numerator graphically. And the difference between the numerator and the denominator is that I have an additional sigma sitting here and an additional sigma sitting there, that if left by themselves will average out to 0. So I need to connect them by paths that are composed of factors of t sigma sigma, originating on one and ending on the other. Right? So in the same sense that what is appearing in the denominator is a sum that involves these loops, the first term that appears in the numerator is a path that connects 0 to r through some combination of these factors of t. And then I have to sum over all possible ways of doing that. But then I could certainly have graphs that involves the same thing and the loop. There is nothing that is against that. Or the same thing and two loops, and so forth. And you can see that as long as and only as long as I treat these as phantom objects that can pass through each other, I can factor out this term, and the rest of 1 plus 1 loop plus 2 loop, etc., is exactly what I have in the denominator. So we see that under the assumption of phantomness, if phantom, then this becomes really just a sum over all paths that go from 0 to r. And of course, the contribution of each path is how many factors of t I have, right? So I have to have a sum over the length of this path, L. Paths of length L will contribute a factor of t to the L. But there are potentially multiple ways to go from I0 to R in L steps. How many ways? That's precisely what I call this 0W of LR. Yes?
Why not a graph that goes from 0 to R in 3 different ways? For example, you can have a path that looks like this.
OK. So you want to have to go from 0 to R. You want to have a single path. And then you want that path to do something like this.
Yeah, that doesn't make any difficult.
That's fine. If I ignore the phantomness condition, this is the same as this multiplied by this, which is a term that appears in the denominator and cancels out.
But you're assuming that you have the phantom condition. So this is completely normal, doesn't matter.
I'm not sure I understand your question. You say that even without the phantom condition, this graph exists.
With the phantom condition,
Yes.
this graph is perfectly normal.
Even without the random phantom condition, this is an acceptable graph. Yeah. Right. So, OK. Yeah.
So what does phantomness mean? Like why then we can simplify to only consider paths?
OK. Because let's say I were to take this as a check and multiply it by the denominator. The question is, would I generate the series that is in the numerator? Okay. So if I take this object that I have said is the answer, I have to multiply it by this object. and make sure that it introduces correctly the numerator. The question is, when does it? I mean, certainly when I multiply this by this, I will get the possibility of having a graph such as this. And from here, I can have a loop such as this. And the two of them would share a bond such as that. So in the realizing model, that is not allowed. So that's the phantomness condition that allows me to factor these things. OK? All right. So we see that if I have this quantity that I have written in red, then I can calculate both correlation functions as well as the free energy, log of the partition function, within this phantomness assumption. So the question is, can I calculate that? And the answer is that calculating number of random walks is one of the most basic things that one does in statistical physics, and easily accomplished as follows. Basically, I say that, OK, let's say that I start from 0. Actually, let's do it 0 and R. And let's say that I have looked at all possible paths that have L steps and end up over here. So this is step 1, step 2, step number 3. And the last one, step like L, I have purposely drawn as a dotted line. Maybe I will pull this point further down to emphasize that this is the last one. This is L minus 1 is the previous one. So I can certainly state that the number of walks from 0 to R in L steps. Well, any walk that got to R in L steps, at the L minus 1 step had to be somewhere. Okay? So what I do is I do a number of walks from 0 to R prime. I'll call this point R prime in L minus 1 steps, and then times number of ways or number of walks from R prime to R in 1 step. So before I reach my destination, the previous step I had to have been somewhere. I sum over all possible places where that somewhere has to be. And then I have to make sure that I can reach from that somewhere in 1 step to my destination. That's all that sum says. Okay? Now I can convert that to mathematics. This quantity is start from 0, take L steps, arrive at R. By definition, that's the number. And what it says is that this should be a sum over R prime. Start from 0, take L minus 1 steps, arrive at R prime. Start from R prime, take 1 step, arrive at your destination R, sum over R prime. Okay? Now these are n by n matrices that are labeled by L. Right? So these being n by n matrices, this summation over R prime is clearly a matrix multiplication. Right? So what that says is that summing over R prime tells you that that is W1, W of L minus 1, 0. And that is true for any pair of elements, starting and final points. So basically, quite generically, we see that W, the matrix that corresponds to the count for L steps, is obtained from the matrix that corresponds to the count for one step multiplying that of L minus 1 steps. And clearly, I can keep going. WL minus 1, I can write as W1, W of L minus 2, and so forth. And ultimately, the answer is none other than the entity that corresponds to one step raised to the Lth power. And just to make things easier on my writing, I will indicate this as T to the L, where T stands for this matrix for one step. Okay? This condition over here that I said in words that allows me to write this in this nice matrix form is called the Markovian condition. The kind of walks that I have been telling you are Markovian in the sense that they only depend on where you came from at the last step. They don't have memory of where you had been before. And that's what enables us to do this. And that's why I had to do the phantom condition. Because if I really wanted to say that something like this has to be excluded, then the walk must keep memory of every place that it had been before. Right? And then it would be non-Markovian. Then I wouldn't have been able to do this nice calculation. That's why I had to do this phantomness assumption, so that I forgot the memory of where my walk was previously. Okay? Now, yeah, question? No? Okay. So this matrix, where you can go in one step, is really the matrix of who is connected to whom, right? So this tells you the connectivity. Right? So for example, if I'm dealing with a 2D square lattice, the sites on my lattice are labeled by X and Y, and I can ask, where can I go in one step if I start from X and Y? And the answer is that either X stays the same and Y shifts by 1, or Y stays the same and X shifts by 1. These are the 4 non-zero elements of the matrix that allows you to go on the square lattice, either up, down, right, or left, and the corresponding things that you would have for the cube or whatever lattice. Okay? Now you look at this, and you can see that what I have imposed clearly is such that for a lattice where every site looks like every equivalent site, this is really a function only of the separation between the 2 points. It's an n squared by, it's an n by n matrix. It has n squared elements, but the elements really are essentially one column that gets shifted as you go further and further down in a very specific way. And whenever you have a matrix such as this, translational symmetry implies that you can diagonalize it by Fourier transformation. And what do I mean by that? That is, I can define a vector Q such that its various components are things like e to the I q dot r in whatever dimension. Let's normalize it by square root of n. And I should be sure that that is an eigen vector. So basically my statement is that if I take the matrix T, act on Q, then I should get some eigenvalue in the vector back. And let's check that for the case of the 2D system. So for the 2D system, if I say that x, y, t, qx, qy, what is it? Well, that is x, y, t, x prime, y prime, the entity that I have calculated here, x prime, y prime, qx, qy. And of course, I have a sum over x prime and y prime. That's the matrix product. And so again, remember, this entity is simply e to the I qx, x prime plus qy, y prime divided by square root of n. Because this is a set of delta functions, what does it do? It basically sets x prime either to x plus 1 or x minus 1, y prime either to y or y minus 1, y minus 1. You can see that you always get back your e to the I qxx plus qyy with a factor of root n. So essentially that, by the delta functions, just changes the x primes to x, at the cost of the different shifts that you have to do over there, which means that you will get a factor of e to the I qx, e to the minus I qx with qy not changing, or e to the I qy and e to the minus I qy with the x component not changing. So this is the standard thing that you have seen is none other than 2 cosine of qx plus cosine of qy. And so we can see that quite generally in the d-dimensional hypercube, my t of q is going to be the sum over all d components of these factors of cosine of q alpha, and that's about it. Okay? So why did I bother to do this diagonalization? The answer is that that now allows me to calculate everything that I want. So for example, I know that this quantity that I'm interested in, sigma 0, sigma r, is going to be a sum over L, t to the L, then 0 WL is t to the L times R. Right? Now this small t, I can take inside here and do it like this. And if I want, I can write this as the 0 rth component of a sum over L tt raised to the power of L. So it's a new matrix, which is essentially sum over L small t times this connectivity matrix to the Lth power. This is a geometric series. We can immediately do the geometric series. The answer is 0, 1 over 1 minus tt, going all the way to R. Okay? And the reason I did this diagonalization is so that I can calculate this matrix element, because I don't really want to invert a whole matrix, but I can certainly invert the matrix when it is in the diagonal basis, because all I have to do is to invert pure numbers. So what is done is to go to the Fourier basis and rotate to the Fourier basis, calculate this. It is diagonal in this basis. I have QR. Okay. And so what is that? These are these exponentials here evaluated at the origin, so it's just 1 over root n. This is 1 over root n. This is e to the I q dot r over root n. This is just the eigenvalue that I have calculated over here. So this entity is none other than a sum over q e to the I q dot r divided by n, 2 factors of square root of n, 1 over 1 minus t, well actually let's write it 2t, sum over alpha cosine of q alpha. And then, of course, I'm interested in big systems. I replace the sum over q with an integral over q, 2 pi to the d density of states. In going from there to there is a factor of volume. The way that I have set the unit of length in my system, the volume is actually the number of particles that I have. So that factor of n disappears. And all I need to do is evaluate this factor of 1 minus 2t sum over alpha cosine of q alpha. Integrated over q, Fourier transformed. OK? Yes?
So I noticed that you have a sum over q, but then you also have a sum over alpha q alpha.
Right.
Is there a relationship between the q and the q alpha or not?
OK. So that goes back here. So when I had 2 dimensions, I had qx and qy, right? And so I labeled rather than x and y with q1 and q2. So the index alpha is just the number of spatial dimensions.
Okay,
if you like, this is also dq1, dq2, dqd. It's
Okay,
a
I
d.
wasn't sure what the index alpha was
Right.
referring to.
Okay. All right, so we are down here. Let's proceed. So what is going to happen? So suppose I'm picking 2 sides 0 and r, let's say both along the x direction, some particular distance apart, let's say 7, 8 apart. So in order to evaluate this, I would have an integral, if this is the x direction, of something like e to the I qx times r. Now, when I integrate over qx, the integral of e to the I qx times r would go to 0. The only way that it won't go to 0 is from the expansion of what is in the denominator. I should bring on enough factors of e to the minus I qx, which certainly exist in these cosine factors, to get rid of that. So essentially, the mathematical procedure that is over here is to bring in sufficient factors of e to the minus I q dot r to eliminate that, and the number of ways that you're going to do that is precisely another way of capturing this entity. Which means that clearly, if I'm looking at something like this, and I'm in the limit that t goes to be very, very small, so that the lowest order in t contributes, the lowest order t would be the shortest path that joins these 2 points. So it is like connecting these 2 points with a string that is very tight. So that what I'm saying is that the limit as t goes to 0 of something like sigma 0, sigma r is going to be proportional to, actually is going to be identical to t to the minimum distance between 0 and r. Actually, I should say proportional is in fact more correct, because there could be multiple shortest paths that go between 2 points. Okay? Now, let's make sense. There's kind of an exponential. Essentially, I start with the high temperature limit where the two things don't know anything about each other. So sigma 0, sigma r is going to be 0. So anything that is beyond 0 has to come from some way in which the information about the state of this site was conveyed all the way over here. And it is done through passing one bond at a time. And in some sense, the fidelity of each one of those transformations is proportional to t. Now, as t becomes larger, you are going to be willing to pay the costs of paths that go from 0 to r in slightly more disordered way. So your string that was tight becomes kind of loose and floppy. Why does that become the case? Because now, although these paths are longer and carry more factors of this t that is small, there are just so many of them that the entropy, the number of these paths, starts to dominate. Okay? So very roughly, you can state the competition between them as follows, that the contribution of a path of length L decays like t to the L, but the number of paths roughly grows like 2d to the power of L. Since we have this phantomness character, if I'm sitting at a particular site, I can go up, down, right, left. So at each step, I have in 2 dimensions a choice of 4, in 3 dimensions a choice of 6, in d dimensions a choice of 2d. Okay? So you can see that this is exponentially small, this is exponentially large. So they kind of balance each other. And the balance is something like e to the minus L over some typical L that will contribute. And clearly, the typical L is going to be finite as long as 2dt is less than 1. So you can see that something strange has to happen at a value where tc is such that 2dtc is equal to 1. At that point, the cost of making your paths longer is more than made up by the increase in the number of paths that you can have. The entropy starts to win. And you can see that precisely that condition tells me whether or not this integral exists, right? Because one point of this integral where the integrand is largest is when q goes to 0. And you can see that as q goes to 0, the value in the denominator is 1 minus 2td. So there is precisely a pole when this condition takes place. And if I'm interested in seeing what is happening when I'm in the vicinity of that transition, right before these paths become very large, what I can do is I can start exploring what is happening in the vicinity of that pole. So 1 minus 2d sum over alpha cosine of q alpha, how does it behave? Each cosine I can start expanding around its q going to 0 as 1 minus q squared over 2. So you can see that this is going to be 1 minus 2dt. And then I would have plus t q squared, because I will have q1 squared plus q2 squared plus qd. So this q squared is the sum of all the q's. And then I will have higher order terms, order of q to the 4th and so forth. Okay? So if I'm looking in the vicinity of t going to tc, this is roughly tc, q squared. This is something that goes to 0. And once I factor out the tc, I can define a length squared in this fashion, inverse length squared. Okay? You can